Okay, I think we can begin. Okay, so for the last 1 hour, so we looked at various ways to solve the vanishing grade problem, right? So just to give you a recap, so we looked at greedy layer-wise pre-training. Then we looked at using activation function like ReLU. Then we looked at a batch norm solution, right? So now we are going to look at how to solve these issues by using optimization techniques. Okay, so now throughout this course, I think the most central learning algorithm that we have been using is the idea of gradient descent, right? So given a data set, let's say a bunch of xi, yi for I is equal to 1 to t, we have at least seen 3 different variants of gradient descent, right? So the first variant was the full batch gradient descent, right? So where theta is equal to theta minus some learning rate times the gradient of your loss function, okay, with respect to the entire data set, 1 over t, y of 1 over t, right? So the idea of full batch gradient descent is to go through the entire data set to compute the gradient. And we already know that this is actually a very slow process, right? And this doesn't allow us to update the model online, right? Sometimes like when you cannot wait for going through all the data, you cannot use the full batch gradient descent, right? However, this full batch gradient descent is actually guaranteed to converge to global minimum for convex functions. And for non-convex functions, okay, can someone tell me like what will happen if I use full batch gradient descent with non-convex function? So what am I guaranteed? Any answers? To local minimum, right? So this converges to some local minimum, right? So now we have also looked at the other extreme, which is the idea of stochastic gradient descent, right? If you remember, in the case of stochastic gradient descent, theta is equal to theta minus learning rate times the gradient, okay, with respect to just one example, xi, yi. Instead of using all the examples, like we are just going to take one example, update the gradient, then next example, update the gradient, right? So now this is useful in many situations. For example, if there are a lot of similar examples in my data set, then full batch goes through all the examples before updating. On the other hand, SGD updates for every example. So I'm going to get better and better, right? So this is usually faster. And this can be used to learn online. I don't need to wait for the entire data set. But we know that this is just an approximation for the true gradient, right? Like this is just an approximation for the true gradient, which is basically x1 to t, y1 to t, right? So this is what we wanted to minimize, but we are approximating it by this gradient, the stochastic gradient, which is a noisy approximation, right? Like, so this is a noisy approximation of the true gradient, right? It's noisy, which means it's going to have some variance, right? Like, so for example, here is an example of SGD training. The x-axis is basically the number of steps and y-axis is your loss. You see that on average, the loss is decreasing, but it has a lot of fluctuations, right? Like it's because of the fact that it's stochastic, okay? Now, even though the stochasticity and fluctuations are problematic, they are also useful, right? The stochasticity actually helps to skip the local minima. Okay, however, it complicates the convergence because SGD can overshoot at some point, right? Like, so, like, even though there are these issues, like if we slowly decrease the learning rate, okay, SGD actually shows the same convergence behavior as batch gradient descent. Okay, now this is the other extreme, but we have also seen something in between these two. Can someone tell me what is in between batch gradient descent and stochastic gradient descent? Mini batch gradient descent, right? Like, so the third idea that we have seen so far is mini batch gradient descent. So this actually takes the best of both worlds. Okay, how? You want the noise so that you can skip the local minima, but at the same time, you don't want it to be extremely noisy, extremely stochastic, right? You want to reduce, you want some variance, but not a lot of variance. So we're going to do that by considering a mini batch of examples, and the gradient update is going to be something like theta is equal to theta minus eta times the gradient, okay, with respect to just n examples, I to I plus n. Okay, so now this actually reduces the variance, okay, which leads to stable convergence. Okay, also, yeah, n random, yeah, so it's true. We are going to sample n random examples. Okay, now this reduces the variance and it has stable convergence, but there is also an additional advantage of doing mini batch gradient descent, which is basically we can use highly optimized matrix operations. Since we are using a batch of data, which is a matrix, we can use matrix operations and train your machine learning algorithms much faster by using GPUs. Okay. Now, this is just a recap of the three variants of gradient descent that we have already seen. Okay. Now, throughout the course, we did not spend a lot of time in understanding the limitations of gradient descent and how to improve that, right? Like we were just taking gradient descent as the default learning algorithm for all the machine learning models that we have seen. But in today's lecture, like we are actually going to discuss the issues with gradient descent and like how to avoid these issues and like how to come up with a better optimizer. Okay, so now let's start with the challenges in using stochastic gradient descent. Okay, so first challenge is choosing a proper learning rate is actually very difficult. Okay, so we have already seen that if you have a too small learning rate, then you have slow convergence. On the other hand, if you have too large learning rate, then you have some hinder to the convergence. Okay, sometimes you can even have divergence. Right? So we need to choose a proper learning rate. Then the second thing is we need some learning rate schedules, okay, to adjust the learning rate during training. Okay, so basically we want to reduce the learning rate according to some schedule so that we can guarantee convergence, right? Like, so after every few epochs, I want to reduce the learning rate. Okay, now how to do this learning rate schedule is a very difficult problem. Okay, so how can I decide? For example, like one solution could be every time you see that the difference in last epoch loss is like minimal, like if you see that the model is not learning at all, like for example, let's say there is some saturation, you change the learning rate, you reduce the learning rate, then you could see some improvement. Then you see a saturation, you reduce the learning rate, then you will see some improvement. Okay, so every time you see that the training is plateauing, then you could reduce the learning rate. Okay, now this is one solution But of course, there is no golden standard here. Like, so like how to come up with learning rate schedule is a very hard open question. Okay. Now, there is also another issue with gradient descent, which is basically you're using the same learning rate for all parameters, right? If you remember, the learning rate eta is fixed for all the parameters. Now, is it a right idea to use the same learning rate for all the parameters? Okay, so it's not right. Why? Because if our data is sparse, okay, and our features have very different frequencies. Okay, so to give you an example, like you guys just finished or almost finishing your third assignment, like where you're looking at sentiment analysis using textual data, right? Like, so now in this case, you have a bag of word representation, right? Like, so where you take 20,000 or 30,000 words and you're representing the entire document using this 20,000 words. Now, this is a very sparse vector, right? Like, so you're going to see one only for some words, and there are actually popular words, like more frequent words, and there are less frequent words, right? Like, so now what will happen is the more frequent words will get a lot of gradient updates, and the less frequent words are going to get very minimal gradient updates. Okay, so now what happens is like there is a discrepancy in the gradient updates if you have various different frequencies for the features. Okay, now how do I solve this issue? Okay, so now these are the three issues that I have listed. We are going to attempt to solve all these issues. So the first issue is the issue of choosing the learning rate. How can I choose a right learning rate? The second issue is how can I come up with a learning rate schedule, okay, which will help me to come up with like better converging models. And the third issue that I have listed here is we are using the same learning rate for all the parameters, which is not reasonable idea. Okay, now how do I solve these issues? So we are going to see a class of or a bunch of improvements to gradient descent. Okay, let's just call all of them as gradient descent plus plus. Okay, something on the top of gradient descent. Okay, so the first idea that we are going to see is the idea of using momentum. Okay, so now to give you an explanation for momentum, so let's say I have a ball that I'm putting from the top of this mountain. Okay, now can someone, okay, maybe if someone can raise your hand, so can someone tell me how would this ball flow from the top of the mountain? Like, so what are the characteristics of this? Can you comment about the speed and like what happens when it starts from the top and so on? Okay, so there's speed and direction. Okay, so what about speed and direction? Any hand raise? Okay, so the basic physics tells us that so Christoph's answer is right. So it will basically speed up, it will build up the speed as it goes on, right? Like, so in other words, it will gather or gain momentum as it goes down, right? Like, so if it is going to move in the same direction, okay, initially it's going to be at certain speed, and since it is going consistently in the same direction, it is going to gather momentum that it actually goes faster to this place instead of going at the same speed. Okay, now we are going to try to simulate the whole, like the same idea with gradient descent as well. Okay, now why do we need to do this? First of all, the stochastic gradient descent actually has trouble, okay, in surfaces which, sorry, which are steep in one dimension than another. Okay, so to give you some example, so here is like a error surface. Okay, now you can see that, okay, if I have to visualize this, like, so this surface is something like this. Okay, so you see that there is a steep, okay, maybe I should have had a 3D view of this. So this is just a 2D contour map, but you can see that this is actually a very like this direction, right? Like, so the X direction, and imagine this is coming out of the paper. Okay, so now this Y direction is actually very steep. Okay, so now what happens here is the stochastic gradient descent, even though it knows that this is the center is the minima, it cannot directly go to the minima. So it's kind of struggling by this. Probably it will take something like this to reach here. Okay, so now SGD oscillates across the slopes of the ravine. Okay, so it's making some hesitant progress along the bottom towards the local optimum. Okay, now how do I avoid this? So this is exactly the situation which could be easily avoided if I use momentum. Okay, so now how do we add momentum to gradient descent? So the basic idea here is to have some momentum term. Let's call it Vt. Okay, so Vt is basically gamma times Vt minus 1 plus eta times the gradient, and theta is given by theta minus Vt. Okay, so now what happens is we are integrating the previous gradients here. Okay, now usually, so this gamma is actually the momentum coefficient. You could also call that as friction coefficient, and this is usually something like 0.9. Okay, now what happens is Vt is integrating the gradients. So if I'm getting positive gradient for a long time, okay, in the same direction, then this is going to integrate over time and it is going to increase the speed of the update. Okay. On the other hand, if I'm going to get a lot of like gradient for like tiny gradients, but like consistent gradient across certain direction, like this is going to increase the step for that particular, it's going to increase the speed in which the gradient descent is moving in that direction. Okay, so essentially this is like using the ball like on the top and pushing it down the hill, so it accumulates momentum as it rolls downhill, becoming faster and faster, right? Like, so that's exactly what this is also simulating. Okay, so the momentum term, okay, it increases for dimensions whose gradients point in same direction. Similarly, if there's a lot of plus and minus, then this whole integration is going to cancel out, right? So it also reduces updates for dimensions whose gradients change direction, right? Or in other words, this helps with faster convergence and reduced oscillation. Okay, so you can see how SGD with momentum works here. So this is SGD with momentum. You can see that it's being very cautious about like the y-axis, but since in the x-axis it is constantly going towards in, the x-axis length is getting larger and larger, right? So it will quickly reach here when compared to this, which is going to take a lot of oscillation. SGD with momentum can actually quickly reach the minimum. Okay, any questions about SGD with momentum before we move to the next algorithm? No questions? Okay, so then maybe I have a question. So let's go back to this ball example. Okay, now, okay, I'm going to have something like this. Okay, now let's say I throw this ball here. It is gaining momentum, right? Now, is momentum the best thing to do always? Like, what happens if the ball has like gains a lot of momentum, that when it actually reaches here it couldn't stop it because it takes time to die out the momentum, right? So it will have a huge momentum towards the right, that you could actually go and end up here, which is not the global minimum, right? So how can I avoid this problem? Any idea? Now what is wrong here? Too much speed, that is true, but how do I avoid that? That's the question. Okay, resetting momentum when the loss increases. Okay, that's a good idea. Anything else? You reduce the gamma term, but then like you get into this tuning the hyperparameter business, right? Like, so now you don't know when to reduce, or what is the right reducing scale, like schedule and so on, right? Okay, now there is actually another smarter way to solve this problem. Okay, so now imagine that instead of pushing the ball from the top, it's actually a human being that you're pushing from the top. Okay, so let's say you are running downhill. Okay, so now when you run downhill, you will of course gain momentum. But then since you are actually seeing the surface, when you see that you are reaching a minimum, you would automatically reduce your speed and slow down in such a way that you don't overrun and you just stop here, right? So what happens here? What happens here is when humans run, like they are not running blindly following the slope, right? Like, so instead of blindly following the slope, okay, we need something smarter. Okay, so if you can have a notion of where you are going, okay, so then you can actually slow down before the hill slopes again. Okay, so this idea was suggested by Nestero, and this is known as Nestero's accelerated gradient, or NAG, as you would see in most of these implementations in sklearn or PyTorch or TensorFlow. Okay, so now the basic idea here is, let's look at the equation. Okay, so I'm going to probably take this equation and move it to the discussion. Okay, probably I copied a lot of extra things. Okay, now let's look at this equation. Okay, now we actually know that we are going to up. So this is something that we have already computed, right? This is from the previous time step. So we already know that we are going to add this to the parameter. What we don't know is the current gradient, right? So how about I peek into the future by first adding this part to my theta and then compute my gradient from the future theta. Okay, so now that is equivalent to a human being seeing what is coming in the front and acting accordingly, right? So the basic idea here is that we know that we will use gamma times vt minus 1 to move the parameters, right? So I can actually compute, no one is stopping me from computing theta minus gamma times vt minus 1. Okay, now this is an approximation. for the next position of parameters. Okay, so now I can efficiently look ahead, okay, by calculating my gradient with respect to theta minus gamma Vt minus 1. Okay, so now the update equation becomes Vt is equal to gamma times Vt minus 1, okay, plus eta times the gradient with parameter theta minus gamma Vt minus 1. Theta is equal to theta minus Vt. Is that clear? Okay. Now, if I have to explain this by using pictures, now let's say this is my current step. Okay. Now, my momentum might say that this is the direction to go. This is my momentum direction. Okay. Now, my gradient says this is the direction to go. So, if you do regular SGD with momentum, okay, then you will basically combine these two things and you will go in this direction. So this is the actual step. Okay. Now, this is regular momentum. Now, instead of this, if I already know that my momentum is like this, okay, then I can go to this plot and then take my gradient step. So maybe my gradient step would say, I need to go like this. Okay. So now instead of, now from the current place that I am, I can actually directly move to this place. Okay. So this is my actual step. And this is not a regular gradient. Let's just call this as look ahead gradient because we moved one step and then we computed this gradient. Okay. And this is my momentum step. Okay. So now this is Nestor's accelerated gradient. And as the name suggests, this basically accelerates the gradient descent process. And typically SGD with momentum converges faster than SGD, and Nestor's momentum converges even faster than the regular SGD with momentum. Okay. So there's actually a question in the chat. Doesn't this method increase the probability of ending in a local minimum? Well, that is true. It is just accelerating, right? Okay, here's the thing. All these momentum or Nestor's accelerated momentum are just accelerating the process. They are not changing the quality of the solution. So you're going to reach wherever you were supposed to reach, which is just the local minima, right? So there is no guarantee that you will reach the global minimum. It is just that this helps you to reach your minima faster. Does that answer your question, Maxim? Okay, so I think this kind of helps us to adapt and speed up gradient descent, right? However, we still haven't solved another problem, which is the idea of adapting our updates to individual parameters. Like, so we still have the same learning rate, alpha or eta for all the parameters, right? Like now, how do I solve that problem? To do that, we are going to look at a bunch of adaptive gradient methods. Which will automatically change the learning rate instead of we manually trying to tune the learning rate. Okay, so the first algorithm that we are going to see is the algorithm called AdaGrad. Okay, now this is a very simple algorithm. The basic principle here is we are going to adapt the learning rate to the parameters, okay, in such a way that we will perform larger update for infrequent parameters and smaller update for frequent parameters so that we normalize the learning. Okay, this is very useful, like if you have sparse data. Okay. So now let me explain. This is a very simple algorithm. Let me explain you how this algorithm works. So let's say GTI is the gradient, okay, with respect to my ith parameter in the tth time step. Okay. So now this is basically gradient of the objective function with respect to the parameter theta I at time step t. Okay. Now the regular SGD update is given as theta t plus 1 I is equal to theta ti minus eta times GTI, right? This is just the regular SGD. Now, what Adagrad is going to do is just not manually, automatically tune this learning rate based on the magnitudes of the gradients. Okay, so we are going to have theta t plus 1 comma I is equal to theta ti minus eta divided by square root of summation p is equal to 1 to t gpi square plus some epsilon, just to make sure it's not division by 0, gti. This is Adagrad. Okay, so what is Adagrad doing, right? So now you can see that this term, right, is basically sum of squares of the past gradients, and then you take a square root. Okay, so now if I have a lot of large gradients in the past, then the denominator is going to be very high, right? If the denominator is high, the learning rate is going to be small. Okay, so let me write it. Maybe I'll first copy this to the next page so that we can look at it while discussing. Okay, so now the effect of this term is basically if you have a lot of large gradients for one particular parameter, then the denominator is going to be high. If the denominator is high, you're dividing by eta by a large value, which means the learning rate is low automatically, right? Similarly, if I have a lot of small gradients or almost no gradient, okay, then the denominator is going to be low. In this case, the learning rate is going to be high. Okay, now the big advantage here is each parameter gets its own learning rate. This is fancy, right? So instead of having just single eta, we still have the single eta, but the eta is adapted based on how big or small are the gradients for this parameter. Okay, now this looks like a very good optimizer. Is there any issues that you can see in this update shown? Any issues? The convergence quality will be bad. Why? Why? Any other answers? Okay, near the local minima, the gradients are small. That is true. Okay, so, well, I think it's true that, Pranav, it's true that near the local minima, the gradients are small, but Gui's comment precedes this observation actually. Like you will, even before you reach the local minima, there is a bigger thing to worry about, which is basically the learning will stop too early, right? Like, so why would the learning stop too early here? Because like, let me list the disadvantages. So both the observations are valid, but the first disadvantage is if the initial gradients are large, okay, which is often true, right? Like initially you start with a random neural network. Now like it's going to have bad performance, right? Like initially the gradients are always large. So if the initial gradients are large, then the learning rate is going to be, learning rate will be low for the remainder of the training. So just in the beginning, like you add huge gradients to the denominator, then that's it. The learning is going to be already too slow, okay? Even if you do some slow learning, due to accumulation of squared gradients in denominator, okay, the learning rate will eventually reach 0 and stop training. Okay, so you know, like going to local minima, yes, if you go near the local minima, then there is this issue that the grade learnings are too low, but that is not affecting here simply because you already have a lot of large gradients in the beginning, which is going to dominate this summation, right? So remember that the summation is from the beginning of the training. So you're going to, this summation is going to be dominated by large gradients from the beginning. And also this is a positive term, right? Like we have G square. So this is always adding some positive value to the denominator. So the learning rate is constantly decreasing. Now, the question is, how do I solve this issue? Any simple changes that we could do to undergrad to solve this issue? Okay, so instead of summing from one, sum just the last k. Yeah, that's a good idea. Okay, so Bruno says last 5. Okay, we can only accumulate gradients from the most recent iterations. Okay, I think they are all a similar solution, right? Like, so yes, you can actually do all these tricks to make this better, but there's actually like a more standard algorithm called RMS prop, which is kind of doing exactly what you guys suggested. Okay, so now instead of having an integration of all the gradients, okay, we are going to have a running average in such a way that you're slowly decaying the effect of previous gradients. Okay, so we are going to use moving average of gradients. Okay, so how am I going to do that? I'm going to maintain E of G square, which is basically some rho times E of G square at t minus 1 plus 1 minus rho times gt square. Okay, now the root mean square of G is given as square root of E of G square t plus epsilon, and my theta t plus 1 is equal to theta t minus eta times RMS of G. I don't need a square, I already did the square root gt. Okay, now this is a very simple modification to undergrad. So all I have done is, instead of using the summation over 1 is equal, summation over I is equal to 1 to t, I'm using a root mean square. So this root mean square is just a square root of moving average. Okay, for example, normally we set rho to be 0.9. If you set this to be 0.9, then you are slowly decaying the effect of previous gradients. So there is actually some constant learning happening, because any gradient that came into this root mean square is going to disappear after some point. Is that clear? Any questions about RMS prop? Okay, so now we're going to look at yet another adaptive gradient method called ADA delta. Okay, now ADA delta comes from a different motivation. Okay, now let's go back to our SGD. In the case of SGD, theta t plus 1 is equal to theta t minus eta times gt, right? So I can also write this as theta t plus 1 is equal to theta t plus some update. Okay, so I'm just putting this whole thing as this. Okay, now in your high school, you would have learned about balancing the units of the equation, right? So let's try to do that here. So ideally, del theta t should have same unit as theta t, right? Because you're adding this gradient to theta t, so they all should be in same units, right? Like, so for example, if you have an equation where you're adding something to something in meters, then your addition should also be in meters, right? Okay, so now if the parameter theta had some hypothetical units, okay, then del theta t should also have the same, right? So let's actually see if this is indeed true, okay? So what is the units of del theta t? This is actually proportional to units of gt, right? Because eta is a scalar. So it's going to be proportional to unit. Eta is a constant, right? So it's going to be proportional to unit of gt. So this is proportional to dou j by dou theta t, okay? We are going to assume that the cost function is unitless, in which case this becomes proportional to 1 over units of theta t. Okay, and now this is a problem with SGD, right? Like in the case of SGD, units doesn't match. Okay, now can you think about momentum and tell me if the units match or not? Any answers? Does the unit match in momentum? If you want a recap of what is momentum doing, it's theta is equal to theta minus, I think it's theta is equal to the way, okay, how did I write it? Is it minus or plus? So theta is equal to theta minus Vt, okay, where Vt is given by gamma times Vt minus 1 plus eta times the gradient. Okay, so now does this term have same unit as theta? Yes, how is it? No, right? So because this term is exactly similar to the gradient as well. So this doesn't match. Same is true for nag too. Nag also the gradients doesn't match. Okay. So now if you remember, like we also looked at another optimization algorithm, which is the idea of Newton's method, the second order optimization method, right? Now let's look at the gradient, the update that we are doing in Newton's method. The update that we were doing in Newton's method was not eta times g. It was actually Hessian inverse times g, right? Where this is basically dou j by dou theta t divided by dou square j by dou theta t square. That is the Hessian, right? So now you can see that this is roughly proportional to the units of theta t, right? So Newton's method actually has correct units for parameter updates. Okay, now this is the observation behind Ada delta. So what Ada delta is trying to do is to correct the units in RMS prop. Okay, so I will just finish RMS like Ada delta and then we will stop. I don't want to stop in the middle. Okay, so now how are we going to do this? So we are just going to take the Newton's method and we are going to rearrange things. Okay, so we are going to rearrange Newton's method. Okay, assuming a diagonal Hessian. Okay, so the update in Newton's method is given as dou j by dou theta t divided by dou square j by dou theta t square, right? So now I can actually rearrange things here and this becomes 1 over dou square j by dou theta t square is equal to this divided by dou j by dou theta t. Okay, so now we can see that in the case of RMS prop, we actually have the root mean square for this term in the denominator. Okay, so now all that ada delta is doing is to add a root mean square for this term in the numerator. Okay, so now the the ada delta update equation is given as the update is equal to minus RMS of this term divided by RMS of GT, and sorry, theta t is equal to theta t minus 1 plus del theta. Okay, now this is just a simple modification to RMS prop. So all I have done here is in regular RMS prop, like you would have just this term in the numerator. Okay, so I think I am missing the eta. So you should also have eta. Okay, so in the regular RMS prop, you just had the numerator RMS. Now we also have the denominator RMS to correct the units. Okay, now this is at a delta. Okay, so probably we will stop here. Like we will continue this discussion in the next lecture. We will see one more optimization algorithm, and then we will also discuss like when to use which algorithm and like how to like what are the other tips and tricks in doing optimization. Okay, so is there any question before I stop the recording? Okay, so if there are no more questions, I'm going to stop the recording.